So now we got discussion time. One of the most obvious things of this experiment when you're looking at this, as we recall, when you get this bottom butanol, you start it boiling, and then when you start to drip this down, you can see how some of the butanol vapor is up in this column. And before this orange liquid even hits the bottom, the orange is already turning to like a green or a brown or a dark. So it obviously proves that your butanol in vapor phase has made it up here. So some of the reaction is taking place here. Now that makes us think of a few things. This whole experiment, we have to really think about this. We are told that we're oxidizing using H2CrO4. When you're given a primary alcohol, whenever you start with a source of chromium-6, oftentimes it likes to oxidize through an aldehyde straight up to an acid itself, a carboxylic acid. So when initially looking at this procedure, without knowing for sure what this particular chromium agent can do, it leads one to believe that we're actually trying to distill the aldehyde out as we form it. So one of the concerns is thinking about whether or not, if we leave this oxidizing agent in here too long before distilling the aldehyde out, that it'll all get converted to the acid. So that's just one of the concerns. So what's interesting is when you go over to, and I actually have straight out of Vogel's, this is one of the experiments exactly that this was modeled after. So our experiment essentially follows this pretty much spot on. And it doesn't specifically say anything about why we're trying to distill it out in this fashion. So then when we move on to Jerry March, one of the Bibles of mechanism in organic chemistry, what's interesting is it says primary and secondary alcohols can also be oxidized indirectly through their esters. Now it says see section 9.20, but in some cases the isolation of the ester is not required and the alcohol can then be oxidized to the aldehyde or ketone in one step. Which is kind of interesting because now they throw in the mechanism. So the mechanism of the oxidation of acid dichromate has been intensely studied. And here's a mechanism proposed by Westheimer, and you can see clearly how they're using this with some acid, right? So that together, that's H2CrO4. There's an alcohol, and it forms essentially what looks like a chromate type of ester, just like you had a sulfonite ester for your thionyl chloride one. So when you have an alcohol, it hooks up with this chromium complex, making a chromate type ester. And then in the next step, they show how, now where exactly is the base? Something in solution, even though it's very acidic, is acting like a base, helping this collapse, kick out the chromate ester. So there you have, in this case, two R's and a CO. You made a carbonyl. So in Westheimer's example here, he's not showing any ester being formed at all. And the way this reads is as if the carboxylic acid is not an issue. It even talks about how here there's three separate lines. It's almost like a different variation of how this can go react with chromium 4, right, to form this radical, reducing to chromium 3. Then you take another chromium 6, and it goes to chromium 5, then the chromium 5 one goes to another chromium 3. So it's almost like he's showing a number of routes. But of course, you're starting with chromium 6. But I'll take another look at this in the results here that shows it's pretty complex what's happening. It's not a very simple thing. So let's just see. Second step, maybe water, some cases. Aha. So, folks, according to this, it's not 100% definitive, but it clearly states that in this case, when we're using this reagent, it's arguably not supposed to make that go to the acid. So then it really makes us wonder, why is it so critical to try and distill it out as we're doing it? So one of the things right off the bat for discussion is, it's just almost begging us, why can't we just add this H2CrO4 without this distilling thing and just reflux it for 3-4 hours to convert all of the alcohol to the aldehyde? And when that is done, then just distill it out, right? So it's a very important question. That's one of the things it'd be very important to try this experiment where we just, reflux it for 2-3 hours and then distill out the product. And the reason for this is it's very obvious that a lot of students, when we're adding some of this, you can see some of the butanol vapor come over. And at least half the students have a lot of butanol in their final product, and it's not pure. So as like an industrial process, if we're trying to make this doesn't seem to make a lot of sense on the surface, so we definitely have to play around with a few other variations. So the other thing, and this is how typically a lot of people in organic write out what's going on. We do look at a yield, and then we even try to look at the chemical reaction. You can see here is we're going to wait for discussion to see a little more on that. Okay. Previous years I posted some discussion threads. Sodium dichromate to chromate and the reaction mechanism. So one of the things that we're looking at here is how do we take dichromate, mix it with sulfuric acid, right? And this is just a suggested mechanism, folks, of how we can arguably end up, right, with essentially two H2CrO4s, right? And I've already alluded to the Jerry March book where we can, I'm just trying to focus that. We're looking at the mechanism. So we already covered the actual method from a book. We actually looked at Jerry March's suggested reaction mechanism. So all I've done is I've taken a closer look in this style, showing how the mechanism might take place. Right? So there you're essentially making this chromate ester, which is an actual sort of an intermediate, and then the last step is having that chromate ester fall apart, and you're left with chromium 4 in this particular mechanism. Obviously, you're starting with chromium 6, right? So Jerry March shows that there's other possible reactions. And one of the things that stands out is if you had 2 sources of chromium 6, you need 3 alcohols to go with it. That's sort of the balance thing. And this just reiterates what Jerry March had shown there without having structure. So, if you had 2 chromium 6s and 3 alcohols, these are the kind of the steps, just like he had in his book, right? So if this suggested mechanism is true, widely studied, but he doesn't say it's confirmed, the idea is you're going to need 2 chromium 6s to go with 3 alcohols. That's sort of the balance thing. So that aside, the color change. Obviously, everybody's seen the orange turn to green, and one of the things is, how does metals produce color? And that comes down essentially to transition metals and how they have, what do they call it, crystal field theory or something like that. It comes down to the d orbitals. And what they're suggesting here is you can have 5 degenerate d orbitals, but as soon as you have ligands or any other type of atom that surrounds the metal, you get a splitting. 3 of the orbitals are lower, 2 are higher, and they even have little names. The top one is EG or EQ, and the bottom one is T2G, if it's an octahedral arrangement. The point is, when a transition metal has atoms around it, you get different energy spacings, and those energy spacings are typically in the visible range, and that's why you have the color. So dichromate starts out as an orange. When you pour some acid in there, you slightly augment what's going on around the chromium, so even the color and the intensity of it changes when you make the H2CrO4, but it still is quite reddish orangish. And then, right, what happens now is when the reaction takes place, you no longer have that chromium 6 and it gets down to something like chromium 3. So obviously what you're seeing now is more of a lot of it's like a dark blue-green kind of thing. So obviously the energy spacing, when you go from chromium 6 after reaction to chromium 3, you're arguably getting a much smaller energy spacing, where the absorbance is now a little more red-orange, and what you're actually seeing left over is the blue sort of green. So that takes care of some of the discussion about color. The other thing we like to talk about is thermodynamics and kinetics of the experiment. This is very typical for any reaction. We've already talked about how you're actually going to form a chromate ester of sorts, right? So you can easily imagine how, let's start over here. This is one of the old ways of doing it here. looking at just organic materials, we know that the alcohol versus the product, just looking at organic, this is slightly higher in energy, right? And we also know that this chromium-6, when it falls to chromium-3, it'll fall down. This is very reactive. So when this is doing its reaction, it's going to kick off a lot of energy. And this reaction is obviously exothermic, because even though you're boiling the butanol, as soon as you add some, initially, a lot of people are like, whoa, you can see how it froths up. So, I mean, obviously, it is quite exothermic. So overall, you have a very reactive species, and as it falls down to whatever it actually is, it's giving off a lot of energy, supplying to this one to take place. And that's quite common. And this takes place quite fast. So the activation energy for this whole reaction obviously must be pretty small, because even at room temperature, this would take place pretty quick, right? So it is very fast. Now, the whole concept of the distillation temperature, I can make a few comments about that, right? And we can also talk about percent yield and purity, right? I'm just kind of showing you what we have here. Whether you can see this is not as important as just talking about it. So the distillation temperature, you know, it's pretty obvious that we have to talk about, as you start having the first distillate come over, it starts out at 82 or 83 or something like that, and as you keep distilling, you start distilling water over. Most of what you added in solution from that addition funnel was water. So obviously the only thing in that flask initially, butanol, some water, some chromium, and then you start the oxidation, you predominantly get butanol, and you start distilling it over. So you obviously stop when you get near 95, because you can see clear as day you're getting more and more water in your beaker, right? So the other thing about the yield, though, is finding out these mystery products. How are we going to account for percent yield? And as always, percent yield comes down to what was our procedure, and where is it possible that any of our organic material, starting material or product, or byproducts, where can it be found? This distilling flask, it's very likely that there's a sizable amount of organic material down here. And the fact that we had one of the past student NMRs that I showed you, that NMR clearly showed leftover starting material in the distillate, as well as two other triplet products that were shifted even further to the right. So some of these students has as many as starting material product and two other byproducts that seem to be intact. So it really opens up the door of wondering what exactly is going on in this reaction, and does it depend on how long we leave it reflux? So long story short, once you account for the yield of what you have here in the beaker, the next big step to get a true percent yield for the reaction would be to do some extractions of this distilling flask and account for what the organic materials are down in here. I mean, and obviously LC is another way to go. If you take liquid chromatography and have a few standards, you can easily account, certainly for the starting material product, how much is in there. So the percent yield, even though we come up with a value, you can use the NMR and the integrals to adjust your percent yield for the alcohol starting material that might be left in your beaker. So you can account for that and fix your percent yield for that. But you can also discuss a little bit about how to get a true reaction percent yield, we have to do some analysis on the distilling flask. So folks, I think as far as this reaction is, those are some of the main ideas of what you would cover for your discussion. So have at it and see what you can do.